So let's just do one at a time. Let's do unit 44 first of all, okay? Start with 1. I'm going to get the copy of the assignment as well, okay? So this is going to take a couple of minutes. Now, the unit pack and assignment information tabs there that I've created, the assignments are on there. So you assignment 2, all you've got loads of theory with regards to this. So let's just open up the assignment. Let's just see, yeah. Assignment 2, yeah. Just give me a minute. All right, let's switch now. My wife's cooking something. It smells so nice. Mm. Can you smell it?
No.
Oh,
I wish. I'm bloody starving.
smells so nice. Wow. Okay. All right, first of all, let's go for task 1. Okay. Improving efficiency, energy efficiency is one of the top things we can do to combat global warming, save money, and improve our quality of life. Okay. Use information gathered from textbooks, internet, journals, magazines, newspapers, and any other reliable sources of information. Discusses the main factors that impact on energy use and efficiency in a building. Okay. So, last week we did a lesson on about building and how to conserve energy within the building, okay, and different technological factors involved. So it says here, discuss some of the main factors that impact on energy use and efficiency in a building. So you can talk about, for example, if you have a building, what energy uses occur in a normal building, okay? You've got many even surprising things as well, because what you've got is obviously you've got electrical energy, you've got your gas energy. We understand that, okay? That's quite obvious. But then you can talk about, for example, how these energies are lost, like due to heat factor, inefficiencies, efficiency of pumps. Okay, so you can talk about different boiler systems that can be used to improve the energy efficiency in the building. You can talk about, for example, some of the main factors that impact on energy use, and so what are the main components that use energy. Like you've got boiler systems, and they're all being weaned out anyway, since the boiler systems next 10 years. They're changing them all. So you've got refrigeration systems, you've got irons, you've got many appliances that use a lot of energy, a lot of electrical energy. Okay, so we need to think about alternatives to these appliances as well. You can talk about these in a list of things that that do take up or consume a lot of energy, and then you can talk about ways to combat energy. To increase energy efficiency. It's actually called energy efficiency, not efficiency. We talked about some of the technologies. You could look at last week's building, and you can talk about that in detail. You can talk about incorporating solar energy on buildings as well. You could talk about heat pumps, okay, but that might come later on actually. Okay, so you can use any different articles you want. What main factors of energy? What main factors consume energy in a building, and how to reduce energy loss in the building as well. So that can be part of task 1A, and that's some of the stuff we did last week as well. Does that make sense, everybody?
Yeah.
Yeah. Okay. 1B. Discuss current energy efficient measures in UK. Statistical evidence should be provided as part of the answers. So look at discuss current energy efficient measures in the UK. This isn't just related to buildings now. It's talking about general. So there's a lot of data you can look on the internet and research about efficiency, energy efficient devices, and believe it or not, motors consume a big proportion of whatever form of energy consumption in the UK. Motors. because motors drive everything. They drive pumps, they drive systems, pistons, turbines. Motors, in fact, are the biggest energy consuming single device in the UK. Therefore, to get energy efficient motors will enable any country in that to save a lot of energy costs from the grid. That's why there's always ways to improve efficiency of motors. There's a new motor out. I don't know if you saw it. It was on the BBC News. A new motor made by Fujitsu, I think it was, to improve motor efficiency. So there's many technologies. Obviously, you've got solar, you've got wind. So you can talk about solar and wind, and you can give analysis how in the UK how much solar and wind is taking over. Because for your information, right now, I received I get these news bites, updates on energy, and I think now solar and wind combined have taken over fossil fuel consumption. Okay, so they've gone ahead of fossil fuel. That's as of now, and obviously there are other implications as well. But what I'm saying is the amount of energy, if you take all the solar energy, if you take all the wind farms in the UK, they're now producing more kilowatts of energy, more than coal. So that's a big issue now, and there's a lot of statistics about that where it can compare with the demographics over the years, how one has taken over the other. And on Teams, then on Teams, if you go back onto Teams, 1 second, I'm gonna click you back on now. In here, there's a lot of information with regards to this as well, which you could just take and you can just grab, okay, whatever you want. I don't want to go through all these slides because they're going to take hours, okay, but there's a lot of information you can grab with that particular activity. Let's go back onto here. So I'm just trying to go back into Word now. Okay, now you might find that some of these things do correspond. That's only because the these assessment targets they cross each other, and sometimes you got to just explain bit one in a bit more detail in a more of a practical way. So that's why some of the questions might correspond to each other. Okay, yeah.
So by measures, it can be either technologies or can it be like schemes and incentives as well?
Yeah, that's good. Measures, very good, well done. And so measures isn't just technology; it's schemes as well. Rules and regulations.
Right.
And on Teams, I put loads of rules, government guidelines and regulations. Okay, so its measures could be technology, it could be procedures, it could be rules and regulations.
All right. Yep. All right.
Okay. I mean, I think there's laws passed in there about what we can import as well from certain countries, and who pollute, certain countries who make a product, and it requires to make that product, if it exceeds a certain amount of CO2, apparently we're not supposed to trade buy that product. It is an alternative and available on the market. I've heard of these as well, but I'm not sure the details of this, but I've heard of this as well. But no one follows them. Okay, energy conservation through energy efficiency in the building has acquired prime importance all over the world. Clearly describe what energy efficiency is and discuss the legislation in the UK that is used in selection of suitable technologies to improve energy efficiency in building or electric vehicles. Now, we did this now corresponds a bit now to this, isn't it? 1A.
Yeah.
Okay, but now it's asking you to gather. This is asking you to describe. Now it's going to a bit more information here. Okay, so 1 second, just looking at something. Oh, there you go. So you've got to look at more in terms of technologies. So you can talk about thermostat systems, control systems, like we did in lesson time. Yeah. You can look at if you can get access to your circuit. Don't know if you've got one, but I put documentation on there as well on Teams of stuff that we did in lesson. So you can go on Teams, you can go on internet, you can search simulation models of energy efficient systems, like central heating control systems. You can put that on there as well. So
But this one,
hey,
you know how it says discuss legislation.
yeah.
So like, can you talk about say like the renewable heat incentive and how that works with like the biomass boilers or like ground
Yes.
source heat pumps and stuff like that?
Very good. That is superb. Excellent. Yeah. And 1A corresponds to 1B because B is just talking about the same thing, but looking at it from a purely technological point of view. So you could talk about the how the components that make up an electric vehicle and why we use them particular components. Okay, that makes sense. You
Yeah.
could talk about DC converters. Okay, so you can talk about converters, and we talked about inverters and converters as well, where
Yeah.
you've got DC converters, and power electronics. You can talk about that as well. Does that make sense, people?
Yeah.
Yeah.
Yeah. And a lot of that stuff I've put on Teams anyway for you. We did it in lesson times as well.
Yeah.
You can give examples of circuits if you want to, but you don't have to go for circuit theory. That's in the next objective that we're going to be doing, simulating circuits, going actual making circuits. So it's up to you what detail you want to describe. The better, the more you do, the better. And technology like sensors for closing buildings, switching lights off. Talk about the types of sensors that they could use. And in buildings, I think you can include that in the top part here actually somewhere. Improve energy efficiency in buildings. Yeah, suitable technology to improve energy efficiency in buildings. So you can talk about technology. You can talk, and don't forget, technology isn't just electronics. Technology is anything to do with innovation to technology. The wheel is technology. A spoon is technology. Okay, so technology isn't just related to electrical technology. It's related to ideas that make human life more function in a more efficient way. That's what technology is. It doesn't have to be just electronics. So when you talk about materials we use in buildings, insulation, okay, triple glazing windows, schemes in the UK to make all the houses double glazed. All the houses in my street, for example, were double glazed by the government fee of charge a few years ago. You have to pay a penny. Yeah, these are all schemes.
Yeah.
They've done a scheme for cavity wall insulation, haven't they, as well?
Yeah, I'm trying to get that. So that's actually really hard to get hold of. Apparently, there's a scheme to change boilers as well, and these are actually quite costly and very hard to get
In
hold
new
of.
build houses, Mo.
Hey,
In new build houses, I think it's 2025. From 2025, you're not allowed to install a gas boiler.
no,
It's
you're
got
not.
to be
I know you're not. It's got to be heat pump or
electric,
or
isn't it?
hydrogen.
Yeah.
And with hydrogen, they haven't got technology for hydrogen yet, because what happens is if you're gonna it's a catch-22 situation. If you're gonna install hydrogen technology as an output to produce it, you've got to use some kind of energy efficient system as well, renewable energy. Am I correct? Now, to separate hydrogen from water, they need a lot of power. And they say if you're going to produce mass hydrogen boilers systems inside houses, we haven't got enough wind power in this country as of yet to produce the power to separate hydrogen from water. Does that make sense? But it's the ultimate, the best way possible is hydrogen technology, because when you separate the hydrogen from the water, you get you get energy which is very flammable. So you use that in order for heating, because you ignite it, and that becomes your element for heating. But to separate hydrogen from because they need piping systems. Now that you can have normal piping systems, they say If you separate hydrogen and water in a plant, you can use the same current water pipes to transport the hydrogen. But when the hydrogen gets into the house, you need other piping. That's not really hard to do. Special piping to transfer that into the house. But to produce that hydrogen in the first place takes energy, and they haven't got enough wind farms in this country. So, but that is the way forward. Now, the problem with heat pumps, okay, the big issue with heat pumps. What's the issue with heat pumps? Anyone know?
That it takes the
Amount of
surface
space.
area.
Hey?
Is it that fact? The fact that it takes surface area to build
Yeah.
it?
You see, heat pumps. If you're gonna have a good heat pump, you're gonna have to have a good insulated house. You can't have the normal houses we have in this country and have heat pumps. They don't work because heat pumps don't produce heat as much as gas boilers do. So you got to have a very well ventilated house, very well in fact, to have a sufficient heat pump. That's the only
Plus, if
issue.
you open the windows, all the heat goes out the window as well.
Yeah, and then the houses have got to be quite complex in terms of how they're built. So what they do now, they build houses cheaper, but with technology involved to make them more energy efficient. So they might not be very robust, might not be very strong. They might not last you 10 generations. Yeah, like the house down the road. Yeah, the whole that no has. But the thing is, but they're good for energy efficiency, and then heat pumps might be able to work in them types of houses. A lot of people who got heat pumps regret it big time. They regret it because the houses are cold all the time, so they have to use other forms of heating to switch to for the heating in the houses. But it's up to them in it really. But anyway, so heat pumps is the best
If they're not that
idea to an
efficient,
extent.
why did
Hey?
they still? If they're not that efficient, why did they still like promote them
Yeah,
then?
this is the thing, isn't it? They're efficient. It's just that I can't extract too much heat from the heat pumps, and so they work, but not to the effect of a gas boiler system. So they've got the other technologies with heat pumps try to increase the heat, and that one of them is obviously digging further into ground. The more in ground that you dig, the more costly it's going to be as well.
Well, what if, say, a row of houses all had heat pumps? Yeah.
Mm.
Would that reduce the efficiency of the actual heat pump at each property because they're all using heat pumps? So they're
Yeah,
all basically gathering heat from the same source, aren't they?
yeah, you're tapping the same source, isn't it? That's the thing.
Yeah.
But the thing is, the heat generated from the earth is so vast. Okay, it's so constant, it's so continuous. Okay, I mean, the chance of that happening is very remote. I mean, not for housing purposes because the amount of heat generated is so continuous from the mantle, so it won't have any effect.
I get you.
In fact, I'll forward you some really interesting stuff that I get. I'll find some links for you and I'll forward them to you. I've got some really good links on all this. I'll just get it randomly. I don't know how actually, to be honest with you. I just get it loads of stuff. Anyway, task 3. Discuss the application of advanced power electronics to small size wind energy and hybrid generating systems. So what you've got to do is you've got to talk about how power electronics is used in wind energy and hybrid generating systems. Okay, I'll put some of that on Teams for you. Now, the PowerPoint, there's a PowerPoint I'll put on for you. Okay, talking about this in more detail. But basically, this is looking at it in terms of the electronics point of view. What electronics is used in what type of power electronics is used. Just you don't have to describe, for example, how the circuits work in detail. Just the circuit operations generally, because the working in detail is more for the next topic. Okay, afterwards, this is just general. So you got something. You got converters. You got inverters. Okay, DC converters, AC/DC inverters. You've got buck and boost circuits as well. Buck and boost circuits. Okay. Buck BUCK and boost BOOST circuits. They're used a lot in power electronics. What buck and boost circuits do, a buck circuit reduces power from one level to another, but it reduces it in such a way where it doesn't use any resistors, so it doesn't dissipate any heat. Because normally when you reduce power, that power that's reduced from that level to that level, electrical power, gets converted to heat energy. That heat energy is what gets wasted. Like if you look at transformers, it's 240 volts going in, 24 volts going out, but the transformers are really hot. Am I correct? In between, yeah? Yeah?
Yeah.
Yeah, yeah.
That's because that energy is lost by heat. In power electronics, we can't afford that to happen. So in power electronics, we use different technologies, different components, where the heat is going from high to low, like buck. It's called bucking or buck circuits, where that heat isn't lost. It's not dissipated through heat. Very clever. And boost is where you got a low power, you want to go to a high power, okay? But you do it in such a way where you're not using too much energy as well. So they're called buck and boost circuits. Okay, so you could talk about them circuits in more detail. And it says they are playing increasing and develop modern wind farms and wind farms. So you can talk about wind energy, how the electronics involved, how it's constructed in a lot more detail. We've done some lessons on that, but I put it on Teams, I think. But you might have to go back a bit. Now, 3B, calculate the energy and cost saving against conventional power sources. Now, some of this, to be honest with you, is the same as in assignment 1. You might take some assignment 1 unit 44 stuff and put it in task 3B. Am I correct?
Yeah.
Yeah. So in it, that happens as well. You might find that happens with units. They cross each other and they're very similar. I think it's to reinforce concepts, and then you can focus the same idea on something else, but this is to reinforce concepts. So you can talk about sizes and costs, and I've put some of that on stuff on Teams as well. But that's easy. That's very easy to get hold of this information here. Okay, it's not really particularly that difficult to get hold of. Okay, it's quite straightforward, easy assignment. This one, to be honest with you. Okay, the more technology, the more circuits you put on it, diagrams. Obviously, it's going to get you marks. It's going to make it look really good, make it look really presentable and colorful as well. Put statistics in there, especially costs and etc. Okay.
Yep.
Everybody okay with that? Yeah.
Yeah, fine.
Rachel.
Yeah.
Very quiet today, Rachel. Hey.
Yeah, just listening.
Okay, no problem. Okay, what we're gonna do, we're gonna go through the other assignment now, which is a bit more technical one, but it's a very easy one as well. It's go back on assignment unit. Yeah, it's assignment 2 in unit 45. Okay, this has got 4 assessment criteria: P3, P4, M2, and D2. Okay, I wrote this assignment last year, so I still remember it. And I remember it wasn't a very particularly huge assignment. It wasn't a big assignment. It depends on how you answer the questions. Okay, so let's just start now with okay, we've got here question 1A. Our college tutor wants to demonstrate examples of energy transformation in transducer-based devices. What are suitable transducers to determine the following effects? Okay, so you got the Seebeck effect, piezoelectric effect, and magnetostic effect. So what you've got here is so you've got Seebeck effect. So you look at where the Seebeck effect is. Seebeck effect is it's thermal and electrical. So you get thermal and you get electrical out. What type of transducer is good for that? Anyone know?
Is it thermistor?
Thermistor. It's actually thermocouple.
Yeah, thermocouple.
Yeah, remember, istor is a resistor. Okay.
Yeah.
Okay. So so this is, in this case, it's a thermistor. So you've got to basically look at the table below of transducers and work, and then you can just work out, basically you can do a lot of research on this, and the more information you put on the how that particular transducer works, its characteristics, okay, the better, not just the name, because don't forget it's a HND assignment, and you've always got to bear in mind you're doing a HND assignment. So even if the question seems very simple, it doesn't mean answering it is going to be simple. Does that make sense, everyone? Okay, and that catches some students out. Okay.
Yeah.
So then you got a piezoelectric effect, magnetistic effect. So you've got to find out what transducers best fit this criteria, and talk about them sensors all in detail. In this case, it's going to be sensors. It's going to be primary transducers, which are sensors.
Yep.
Okay. Okay. 1B. Select any transducer from the question below. Draw the interface requirements of the transducer if the transducer was to be connected to a microprocessor. So what you've got to do, you've got to take you've got to take any transducer, any of these transducers, doesn't matter which one of these are. Say for example, you take the thermocouple, okay?
Yeah.
Now remember, I gave you a circuit on thermocouple transistors. I'll show you, in fact, if you remember. I'm going to go back into Teams now.
Yeah.
When I get it, I'll share it with you. Just give me a second. I've got it. I think I've got it. Was this it?
Oh yeah, I think.
Was it this? Was it this one? I did actually give you a thermocouple somewhere. Sure, I did. H-bridge connection. This is motor speed. Wait a minute. Let me go back a week. One second. Oh, I gave it to you. Oh yeah, there you go. So they got your thermocouple here. Yes, this is a circuit for a thermocouple. So you got your filter circuit, you got your thermocouple, you got an amplifier because you got to amplify the signal. Otherwise, you won't be able to read it because it's in millivolts anyway, the output. And then it's an analog signal, and then you put that to some kind of analog digital converter. Okay, then you can connect that to a microprocessor. But microprocessors do actually have analog digital conversion systems. So you can put an analog signal to a microprocessor, and it has ADC systems within inside microprocessors. Like in PLCs, they have them inside built in already. Okay, and you can also give an example of a circuit that's an ADC converter, because you can, if you don't want to use a microprocessor, you can use a circuit, and you can go in more detail, and you can talk about what circuits you can use, what type of ADC circuits there are on the market as well. That makes sense, everyone, yeah? Because there are many different types. And this is an example of an analog to digital converter here. You've got a voltage going in, and depending on the voltage level, you're going to get different volts here going out. Like if you've got full voltage, that output's going to be high, that's going to be high, that's going to be high, that's going to be high. So all 4 LEDs are going to be on. If it's a low voltage, only 1 LED is going to be on. So that's analog and digital system here. Does that make sense, everybody? Yeah.
Yeah.
And so you could, for example, have you could put that circuit here, and then these outputs could go to inputs to a microcontroller, and a simple program, you can just write down which LEDs, which outputs to switch on. These could be motors as well. It could be anything really. It doesn't have to be lights. It could be anything you want really. Outputs here. Does that make sense, everyone?
Yeah.
Yeah. Any questions about that?
No.
Yeah. So you've got different ways you can do it. The more circuitry you put on, I guess it is going to be better for you. Okay. Let's go back to the assignment. Share the teams. 1 second. All right. Let's do this one. An industrial automation setup uses a variety of modern control and automation hardware devices and equipment. Due to use of various proximity sensors throughout the building, the heating of the main production line must be automatically set to a certain threshold in order not to interfere with optical sensors and other devices which may be affected by too high or too low temperatures. You get that in automation environments. The temperatures of the factory floor has to be set such a way where it doesn't interfere with sensors. Okay, so you've got to have maintain a certain temperature all the time. Okay, select a suitable primary transducer input to the control system. So what type of sensor would be used, for example, to control the heating environment of a particular of a shop floor of a production floor area? Now you might be tempted to say thermocouple, or you might be tempted to say thermistor. Okay, so you've got to find out which is best, thermocouple or thermistor. But there are other devices as well, the RTD, yeah, resistant temperature devices. Okay, so you got different types of temperature devices, and so you can look at that and you can see which you think might best suit. Draw a control system block diagram which will illustrate the operation of the automatic temperature control system using a PLC. The heating element is driven by a 240 volt source. So basically what you've got here is this one here. Read it carefully.
Yeah.
So you've got like you would have in normal real life application. A PLC is going to be controlling everything for you. Okay. Now, so you got your sensor going to the PLC. Now, you're trying to maintain a certain level, so you're going to use a HDMI connection. Yeah, the HDMI. You're going to use yeah, HDMI. Do you know them screens and panels? Yeah.
Right.
So you can set your temperature on there. So that you can include that in this control diagram going to the PLC, and then what will happen is the output will go to relays, which will switch on, say, a heating system. Now, and then the heater itself, what will happen is, so as the heater goes hotter or it goes colder or whatever, a sensor will detect the temperature, the ambient temperature in the environment, to make sure to switch on and off the heating system. Does that make sense, everyone?
Yeah.
Yeah. You can make it as detailed as you possibly can. Okay. And it says the heating element is driven by a 240 volt AC source. So you've got to include a relay. So in your PLC, you've got to include relays. Yeah. We did some stuff on relays a bit. Okay. Do you all know what relays are? Yes.
Yeah.
Yeah. Okay, so you've got to make sure you include, and it's not any type of relay as well, because you've got to look at thermal protection relays, safety relays. Got to be careful what relays you use as well. Explain your choice of sensor and illustrate the main data blocks which would be required to produce a suitable program. Take into account output interfacing for the heater. So what you're going to do is, you're not going to write the program, because I don't want to, but just write down the main blocks you would use to be able to write the program. Okay, you don't have to write the full programming ladder, just the blocks, like a flow chart or something. Does that make sense, everyone? Yeah.
Yeah.
And it says you take into account output interfacing for the heater. Okay, so there'll be relays that you're going to switch on anyway, so it'll be relay system. Now, a little hint here. You need to have a safety device, a safety off switch. To switch it. Say anything happens, okay, because it's all connected to the PLC. You've got to be able to have a safety device. Now, what's the most dangerous item going to be here?
Is it the heating element?
It's going to be heater. It's going to be the heater, yeah. Now, you might need to include a fan as well to extract the heat, because you don't just have heaters, though. You have fans. So you might need to include a fan as well in your diagrams as well. because the fan must only come on when the heating comes on. The fan doesn't come on, the heating can't come on as well, because it's dangerous to have just a heater. If you have a standalone heater, it's quite dangerous. Okay, so and then you've got to have some kind of ventilation system for air to cool down the heating. But it says here, what was it? Technical account of interface methods for the heater. So you've got the relay for your heater. Yeah. Now, question: if you're going to have an emergency stop, where should that be placed?
This the most accessible place.
Yeah, but what should it be connected to?
The heater.
Yeah. Now,
Right.
not to the PLC. Yeah.
Not to,
Now,
yeah.
why would you not connect an emergency stop to the PLC if you want to switch off the particular output device connected to the PLC? Anyone know why?
Is it because you'll have to like run a program first before?
Exactly. And the program could crash. There
Yeah.
could be a bug in the system. Am I correct? So if you want to say you got a motor, you want to quickly switch it off. The last thing you want to do is go for the PLC program to switch it off, because there could be a problem with the program and it might not work. Okay. There's two emergency stops. There's one for the PLC program as well, and there's one for the actual main any device that you want to isolate.
Yep.
Okay. And then also, when that emergency stop's been activated, a signal from the output of that stop goes back into the input of the PLC, and on the HMI you can say emergency stop's been activated. Does that make sense?
Yep.
So you got some kind of feedback. So you're telling the PLC, okay, this has been activated, not to get permission, but to tell you it's been activated. So you know, so you would know whether to continue with an operation, or not continue with an operation. Okay. So does that make sense, everybody?
Yep.
Now, there's some really good circuits. I'm going to put some on Teams for you, okay, regarding emergency stop setups for PLC. I'll put some on for you today. In fact, I'll just do it after the lesson. Okay. So you see, these questions look very simple, but you can make them very detailed as well.
Yep.
Okay. Let's go to this question here now. Design a circuit which would allow the reading of both tension and compression on the above strain gauge. The measuring device is an analog voltmeter which has a reference of 0 volts ranging from plus or minus 10 volts. Take into account impedance mismatch of the circuit. Describe a practical application of the circuit. You will not require to include component values. All right, what have you got here? You've got here a pressure sensor, and you've got here a Wheatstone bridge. So you've got to connect that pressure sensor. You've got to redraw the circuit to connect the pressure sensor in a Wheatstone bridge. All right, thank you. So you've got to put that pressure sensor into the correct input of the Wheatstone bridge. This is the output here, okay? So you're going to get an output here within the range from measuring device and analog. Now listen carefully. Look at the wording. This is a bit tricky here. The measuring device is an analog voltmeter which has a reference of 0 volts ranging from plus or minus 10 volts. Okay. Now that's a measuring device. It's not the output of here. Now you'll find that an output for a Wheatstone bridge is very minimum. So you've got to include an amplifier. You okay with that, yeah?
Yep.
Now with that amplifier, you've got to include something called a buffer. Remember this, guys, okay? Because I had all these practical lessons set up for you to do all this in the lesson, but it's not particularly hard. It's just an amplifier and a buffer. Now, what the amplifier does, it amplifies the signal. What the buffer does, it makes the impedances, because it says here an analog voltmeter. Now, if you've got a digital signal and you've got an analog device, measuring device, there's always something called an impedance mismatch. You're not going to get the same value as you would do with a digital meter. It's a natural thing, it happens. So you have a buffer, and that makes the two impedances then match together, so to give you the correct value. So it's called the buffer. You've got an amplifier and you've got a buffer, then you've got your output measuring device. Okay. Then it says describe a practical application of this circuit. Now, obviously, it can be used in weights, like in kitchen scales, measuring drugs, for a gangster, okay, because they're quite sensitive devices, okay. So the different ones, okay. So it's up to you. Now, that's not advice, by the way. Now, you can have two, or you can have one, or you can have two. The more strain gauges you have in a Wheatstone bridge, normally you have one. That's the simple, cheap ones. But you can have two. The more sensitive it's going to be, and so you've got that system as well. So you can research about Wheatstone bridges having multiple transducer devices, and so that's quite easy to do. So yeah, it's going to be a sensitive weighing scale, digital weighing scales, for example. Okay, but it says here tension and compression. So what would that be then? Anyone?
Don't know.
Okay.
I don't know either, really. Tension and compression.
Okay, what you've got is now. It gets confusing, okay? Because when I get confused between these two. Even now, after all these, people get confused. When you put your foot on something, okay, you're creating compression. So a normal, like a weighing scale, is compression. Now tension is the opposite. Now, say you've got a bridge, okay, and the bridge itself is subservient to wind, and you've got to make sure that there's not too much wind that's bending the bridge in the wrong way. So you actually have these sensors attached to bridges to sense how much of the beams of the bridges have been bent. That's tension. That makes sense, people? And then the warning lights happen and all this stuff. Then the bridge gets closed if the beams are bending too much or the bridge is bending too much. Okay, that's an idea, an example. Does that make sense, everybody?
Yeah.
Yeah. These are practical examples of strain gauges. They use the bridges a lot. They're using weighing scales a lot as well. Okay. Now, let's look at this question here. What does it say? All right. So what have you got? First of all, you've got a door. This is a submarine system. It's using a hydraulic system. You've got liquid here, reservoir. That's your door. So what you've got here is this door. So this is spring return. So it's keeping this closed. So when you push the lever, what's going to happen? It's going to force the door to go open. It's going to force the spring to go in, and then it's going to force the door to go open. Basically, it's a hydraulic based door closing system using submarines, because submarine doors are really heavy, and you can't open them and close them by hand efficiently. So you need to have some kind of a system to be able to, maybe hydraulic or pneumatic system, to be able to do that. Okay, so that's what this system here is. Now, so this is what you have to do here. An enclosed research facility has issues with air quality due to nature of its operation. Ooh, okay. When the air quality deteriorates below a specific threshold, a heavily sealed door will operate and allow fresh oxygen to re-enter the facility. Also, this isn't a submarine, okay? This is taken from a submarine. The door will close when air quality resumes to suitable standards. The entire operation is automatically controlled. A hydraulic-based actuation system was initially planned as above, but it was felt a pneumatic system would be more appropriate. Okay. One of the reasons, why do you think in this situation I've chosen a pneumatic as opposed to a hydraulic system?
Because it works off air, pneumatics, on pressure, I mean.
Both do. They're both similar concepts. They're both very similar concepts. Look carefully. It's a clues in the question actually. I had some students who couldn't figure this out actually, even and then it was when I gave it to them, they thought, oh bloody hell, it's so obvious. Look carefully, okay?
Because it's submarine.
This is not. This is because it's something. But why have I said that this system of hydraulic is better to use pneumatic rather than a hydraulic system? Look carefully. When the air quality deteriorates below a specific threshold, heavily sealed doors will operate and allow fresh oxygen to re-enter the facility. Now, what we're talking about here, we're talking about speed of operation. Because if you've got air quality that's going to deteriorate, it's going to be bad for health. So you need something that can extinguish the good from the bad to act quickly. Now, hydraulic systems are slow. Pneumatic systems are really quick. It's speed of operation. Okay.
Yeah.
Now let's see what the questions say. Modify the above diagram to a pneumatically controlled system using components, symbols, and necessary schematics. Okay. So, just stay with me for a second. Okay, I'm gonna open one or two things up for you now. Okay, just bear with me, yeah? I'm gonna open up a document for you. I'm gonna put this on Teams as well. So I'm trying to switch something on to Teams. I'm just finding it hard to do. One second, I'll do it again. Yeah. No, that's the wrong page. Sorry, it's the wrong page. Just bear with me, okay? I'm not sure if you can see this page. I'm going to put this on Teams. What you've got here, this is your actuator. That's your control valve. It's an electro-pneumatic. You've got your wire here. It's spring returned. Now, the way you design that is this way. So you're going to go through a relay. It's going to switch on the solenoid. You all understand that, yeah?
Yep.
Now that could be an output to a PLC, switching on the coil, switching on the contact, switching on the solenoid. If you do it this way, it's not a good idea because you might not get enough current from the PLC to switch on this. And even if you get enough current, you get back EMF because it's a solenoid. You get back EMF, and that back EMF can switch on anything that's connected before. So we do everything through a relay. And with a relay, you can add additional power sources. Any back EMF, it's not going to damage whatever switched on the relay. Does that make sense, everyone? Yeah?
Yeah.
So that's like, it's just a lot safer to do. So that's basically that. So so maybe you drove this type of circuit, exactly this, in fact, okay? And you drove this type of K5 is, forget K5 for the time being. You don't need that. So you got your start button here. And then that could be an output from a PLC, like Q0.0. When that's on, then do that. Okay, but yours is going to be controlled both ways, open and closed. So you're going to have something like this, but not quite this. You're only going to be using probably one solenoid, so one actuator. So one output of the PLC would switch it on. K1, that will make this switch on. When that extends out, it will maybe a sensor could be attached to here, like a switch, and that will be activated coil K2, and that will be Y2, not Y3. Does that make sense, people?
Yeah.
Because you're not using that, you're going to be using that. You're just going to be using Y1 and Y2. So that'll be a Y2, not Y3.
Have they called it Y3 because they've used Y3 for this second?
Yeah, that's exactly. That'll be A plus, B plus. Yours is going to be A plus, A minus.
Yeah, yeah.
Okay, and that's an example. Okay, you can add on to it if you want. You can add on a different sensor, because you can put sensors instead of switches. Remember, sensors are 3 coil devices, 3 wired devices. You got your power, then you got the output, and the output of the sensor activates a coil, whatever you want to call it when it activate, and that coil will switch on anything you want to switch on, any solenoid you want to switch on. Okay, so so this is a really good document, and I'm doing this with my BTEC level 3 students. This in a lot in detail in electro-pneumatics, because it's electronics is one of my strong points. So I'm doing this. I'm going to give you this document as well. So if you go back into the assignment now. 1 second. I'm going to try and switch this off and switch it back on again. So that's that part there. Just redraw the circuit basically. The system will be, so that's just drawing a circuit as I showed you, without any, just like a normal switch. Just redraw this and then connect it to a door. Do you understand? You're not using any PLC. You're not using anything like that. Okay. Okay. You're just redrawing that. But then it says here, the system will be controlled using a PLC. Show how the pneumatic system can be controlled using PLC of your choice. Take into account output current restrictions due to the use of electro-pneumatic solenoid units. Okay, so that's connect it to a PLC and just show it what it would look like. Now this part is a bit tricky. Select a suitable transducer to monitor air quality and include any suitable interfaces required to allow full integration to the PLC. A detailed circuit diagram was not necessary, just a schematic overview. Now, you've got to find sensors that detect air quality. There are sensors that detect air pressure, but we're not talking about that. There are specific sensors that can detect purity of air. There's one sensor that detects the amount of oxygen in air. There's one sensor that detects the amount of dangerous particles in the air. I'm not sure what it's called now. Students gave me a list. There's so many sensors you see nowadays for everything you forget. But you've got to find one that you think is suitable, that will match the assessment criteria and explain the reason why. Because the sensor that detects everything, trust me. Okay, you just got to find a suitable one. Find a control circuit. And some of them don't actually have, you don't need to have an interface circuit. They're already built. You just connect them to a PLC directly, some of these, okay? But you can get a schematic of the diagram of the sensor inside, and that'll be good for your assignment as well. So, does that make sense, everybody?
Yeah.
Yeah.
Yeah?
Yep.
So I'm gonna put that other document on Teams as well. Now, any questions? Do any of you have any questions?
Not yet. I'm sure I will at some point along the way.
Sure you will. Look, try to get done as much as you can. I've made it quite comprehensive for you, okay? I mean, the way I've answered it, and I'm going to put some stuff on Teams as well to answer it, to help you answer it even more. So hopefully you shouldn't really have any problems. I had some stuff on sensors as well. This part here, I had some catalog pages on sensors that you could use. I'll try and find them. Because when I transferred my files from last year to this year, a lot of work for different units got missing, and a lot of really good stuff, really good, really top-notch stuff for the HND units got misplaced as well. And it's going to be somewhere, but I can't find it. So I'm going to try and find some catalogs for sensors for these. Okay.
Yeah.
But
Yeah.
if you need anything, just let me know. I'm always here. Okay.
Yeah.
So I'm just gonna go. What I'll do is I'm gonna download this video afterwards. When it downloads on here, I'm gonna put it on YouTube. So I'm gonna give you a link to YouTube because it'll disappear after 10 days. Yeah.
Yeah. Yeah.
Okay, we'll stop recording.